Headset is not pointing to. Okay, it's all working now. Um, all right. So a few things. The first one is um, where's my mouse? There we go. So the first one is a document that is generated 100% using ChatGPT, but it is a summary of a long conversation that I have had with ChatGPT. It made some suggestions, references to the material, and I double checked. Okay, I don't just say, okay, if ChatGPT says so, it has to be the case. Okay, I actually checked the references that it refers to. So the document has to do with, the mentioning or the explanation of five key dimensions of thinking and problem solving that shape success in the computer science or computer information science field. In other words, these are the things that will probably be important in your career, in the long run. Okay, or at least, I do agree with, the assessment that these are actually useful things that you need to kind of master. So now we move on to the sections. If you guys are interested, I can share the document through the announcement. Otherwise, it's just like, okay, Tech just wasted 10 minutes of the class time, and that's about it. So the first one is an explanation of the five dimensions. One dimension is called analytical depth, which is how well can you break up a large problem into smaller problems. Okay, so you're given the task. Your car is not starting this morning. Okay, what do you do? Okay, call Uber, right? That's the immediate solution. But what do you do to fix the car? Well, you kind of have to think about, okay, what are the symptoms, right? What are the subsystems that need to function in order for your car to start? And then you check each and every subsystem. Okay, if your car is not making any sound at all, there's no clicking sound whatsoever, everything is dead, dead on the dashboard. The first suspicion is the connection to the battery, or the battery is completely dead. Okay, so you use a multimeter, right? You go check out your battery, everything is good. Okay, if the battery is good, then somehow power is still not delivered to the rest of your car's system because your dashboard is dead, right? There's no sound whatsoever. So the next prime suspect would be the fuse because that is in series with the system. So you just check every single point along the way. So that is analysis. Okay, you're breaking down a big complex problem into smaller steps, whereas for each step, now you can actually do something about it. You can check. Okay, now we did not mention anything about fixing it, but at least you can help. It will help pinpoint the problem. The next one is called abstraction capacity. Well, everything in computer science, everything about code development is about abstraction. Vibe coding is about abstraction because what you're doing is instead of describing exactly how to do something concrete, you're describing the general method of how to do something. Okay, so that's abstraction. Every time you use a class in object-oriented programming, that's abstraction. Every time you copy and paste and you get that really kind of gnawing feeling in your head, it's like, that's not the best way to do it. There has to be a better way instead of copying and pasting. That is abstraction. Okay? So computer science, generally speaking, mathematics, generally speaking, is all about abstraction. Yep. Oh, you mean the mechanism of abstraction, like, classes? Hmm. Yeah, so using an abstraction, sometimes you don't have a choice because you have to interact with, let's say, Google Maps, the API, or OpenAI as an API. So you have to use their abstraction, right? So you have to use their interface to the system. But when it comes to your own code, okay, understanding that, hey, this section of code has a resemblance to this section of code, and try to extract both sections of code, turn it into a method or a function, and then the only differences would now be expressed as parameters. That is what you are talking about, right? That's quote unquote creative abstraction because you're making the abstraction yourself out of your own code. Yep, so you're correct. The third one is called technical precision, which translates to, in programming or in code development, it translates to understanding and being able to use the syntax correctly. Okay. Um, Now, does it mean we have to be perfect every single time when we write a program, not to make a single mistake in syntax? No. Okay. It just means, generally speaking, you don't spend too much time making mistakes in the syntax and have to fix the syntax errors afterwards. The next one is called integrative reasoning, which is, I would call this cross-domain reasoning. Okay, so let's just say that you like cooking, okay, of all things, okay, you enjoy cooking, and you learn in your cooking, experience that sometimes when things don't turn out the way you want it, okay, you have certain ways to diagnose, okay, to find out why it's not turning out the way you want it. And then you find that, hey, this technique that I use in my cooking can also be applied to programming. If a program is not working, I can use kind of the same approach to find out why the program is not working. So that's cross-domain reasoning. Skills that you learn in one domain, you can apply that in a different domain. Okay, that's integrative reasoning. And then the last one is called metacognition, which has nothing to do with Mark Zuckerberg and his company. This has to do with being able to step back and look at yourself thinking. Okay, so let's just say that you spent a lot of time to debug a program that you wrote, okay, for CISP 430, whatever. Okay, so instead of just being done with the program eventually and go like, oh man, that was rough, and I can now rest. Okay, instead of doing that, you take a step back and you ask yourself, why was it so difficult? Okay, why did I make a mistake over here? Was I making the wrong assumption about something, or was I neglecting about something? Or was it because I didn't test all the functions that this particular function is calling, and therefore, if the called functions are faulty, then the caller is not going to be able to do what it's supposed to do, right? So you take a step back into your own thinking process. In other words, you are debugging your own thinking process. Okay, being able to do that goes a long way. Okay, because it really speeds up how you learn things and how you make mistakes only once, because you find out why and how you make the mistake to begin with. So generally speaking, I think making mistakes is great because every time you make quote unquote a mistake, you have a learning opportunity. Okay, as long as you reflect on it and figure out, how did I make that mistake in the first place? Okay, so anyhow, these are the five dimensions. And then the second section talks about the importance of these five dimensions across the career path. So for most of you, you're probably more interested in the entry level. But as you move on in your career, you can see how some of the dimensions become more useful later on. And if you want to become an educator or consultant or leadership, there are also your particular dimensions that are really important in those. The next section, section 3, gives you a table. Now, this is a very interesting table. I find it very interesting, and I find it very important as well. So, what this table is telling us, okay, is if you just take Joe, who is the average person in the computer science industry, okay, and say, hey, Joe, how smart are you? Joe goes like, I'm just average among my peers, okay? But if you take Joe and compare Joe to the general population, Joe would be at the 82 percentile when it comes to analytical depth. Joe would be at the 82.5 percentile in abstraction capacity, and so on. So Joe is not average at all when you compare Joe to the general population. Okay? Why is this important? From your perspective, you'll be competing with Joe for a job. Okay, that's a valid reason why this is important. What do you think is the average for CISP 300, the entry level class for the computer science degree. They'll be probably at 50 percentile because as a community college, we do not have entry requirements. Okay, we don't say, oh, if you don't have a GPA from high school of 2.5, okay, you cannot start your classes here. No, there's no requirement. Everybody can just walk in and say, hey, I want to enroll in CISP 300. Okay, you're in. So that means in CISP 300, not in this class. Okay, uh, the class average is probably at 50 percentile. So now the question is, how do we cover the 32.5%, the 32.5%, the 37.5% of difference? Well, okay, if you're thinking along that line, that's exactly what you should be thinking about. Okay. Now, I'm not in any way saying that you guys or any individual in this class is at 50 percentile, but I'm saying that at the beginning, almost everybody or the average of CISP 300 is probably really close to 50 percentile. Okay. So the next section is also important because of this, because it tells us how much of each dimension is innate and how much of each dimension can be acquired by education, which is why you're here. All right. So we'll take a look at these, and you can see that except for one, the other four are just medium high, low medium, which is basically just non-existent, medium and low medium. They are not inborn. Okay. Most people are not born with those particular competencies. They are all learned. The only one that may be difficult for people to acquire, after is abstraction capacity. Now, I really cannot tell one way or the other because, I just like what I do. So I really do not know how much effort I have put into, studying computer science and all kinds of stuff like that. So I have no idea how much of mine is innate and how much of it is educational because, to me, taking classes in computer science when I was a undergraduate student it was like going to a theme park to most kids. It's like, okay, field trip today again. Yes, okay, teacher, teach me something new today. I actually went to class with an attitude like that every day when I was an undergrad. So anyway, you can see how most of these items can be acquired later on. Okay, analytical depth can be learned. Abstraction capacity can be learned to an extent. Okay, technical precision is all about what you learn and how you practice it. Integrative reasoning can be learned, and metacognition, once again, is something that you can learn to do in a pretty, in a significant way. The first thing is awareness. Okay, once you're aware of metacognition as a skill set, as a competency, then you can look it up, right? You can look it up and say, how can I practice this? You can set a reminder to yourself. Okay, hey, I need to look back in my own thinking process about learning something, about doing the homework assignment. Okay, so it's about awareness too. The last section is basically what okay, when I say we, I'm talking about instructors and the college as a whole. This is what we are supposed to do. Okay, is to help improve each dimension. Okay, to help you to improve in each dimension, and has some suggestions that are actually it's more intended to you to do. Okay, like for analytical depth, practice breaking large assignments into subtasks, work through debugging systematically, and so on. And guess what? You will have opportunities to debug some gnarly code, uh, maybe in week 10 or so in this class. You will get that opportunity. I'll remind you of this when we get to that point. So if you think this is useful, let me know, and I can send this little um, thing to all of you via announcement. If you say this has nothing to do with what I want to do here, that's okay too. I'll just kind of go like, okay, we just wasted about 15 minutes of time, not so much to you. um, and that's it. So I'll let you guys think about that, and at the end of the lecture, you can let me know, which way you want to do it. This is also kind of interesting. This one is about tools for taking notes. Many of these are open sourced. I can also share this link with you if you are shopping for note-taking tools. So once again, that's also up to you, because if you say I got a really good system taking notes already, thank you very much, but I don't need another thing, that's all good. On the other hand, if you go like, oh, I want to take a look at what is available out there, as alternatives, then I can share this document with you as well. I mean, this is just a link. Somebody wrote it on GitHub. Are we good so far? Good. All right. And generally speaking, if you say I need to learn how to take notes, I also have some pointers, in my own modules. So if you go to, I cannot remember where. Oh, I may not even have it here. I'm surprised. Huh. Oh, the practice tab, this one? Yep. So I can open all of these for you guys to practice because these are the ones that we have done already. So that means, if you want to go like, okay, I'm not really sure that I got all the things about base conversion down and I want to practice a little bit more, now we can go to this activity and practice as much as you want. All right, cool. And today have we done addition already? I think we did. Yeah, so I'm going to open addition as well. So now we can practice, using these exercises. All right, so that's all the stuff that I wanted to kind of bring to your attention that is not exactly in computer architecture or assembly language programming, but I just thought some of these items may be helpful to some of you in some way. Yes, that's awfully vague, and I want to keep it that way. That's legal talk, so I won't be held accountable for actual outcomes. All right, so we are now moving back to the topics that we need to talk about. We are currently on this one. We are done with binary addition and subtraction, I believe. I think we did subtraction already. Yeah, we did subtraction, and I finished a. Did I finish the adder, the 3-bit adder? Yep, yep. Okay, so that's all done, and I hope you guys got an idea of how the relationship between digits in a multi-digit addition in base 2 relate to the circuit. Okay, once we know the relationship as equations and formulae and whatnot, we can translate that into actual circuits performing base 2 multi-digit addition. So that's the whole purpose of that exercise from last class, on Thursday. All right, so at this point, today we are, oh, addition is here. We haven't done addition yet. So we haven't done addition, so I have to retract the other addition. So I have to unpublish this one because we actually have not done the actual lab that counts for points. So now that's what we'll be doing today. That's what you'll be doing today in the lab. But we are moving on to signed versus unsigned representation in terms of the class content. So let's go ahead and check this out. All right. So the first section talks about finite width bit width, which basically means when you use the word int in CISP 360, that's not actually integer, okay? It is integer with some restrictions. Um, the integers can be 16-bit wide, okay, which means there are 16 binary digits in an integer. It can all the way out. It can be all the way out to 64-bit wide, which means you have 64 binary digits. So since we have already talked about base conversion, does everybody understand what I mean when I said, oh, your integer is 16-bit wide? There are 16 binary digits in the integer. Do we understand what that means? All right, cool. So now what we want to do is to take a look at what do we know about the range of integers? Okay, because when you ask a mathematician and you ask, so what is the largest integer? Okay, the mathematician will come back and say there's no such thing. Okay, let's say you say, but what about k? This constant k here is the largest possible integer. Then the mathematician would come back and just give you a really snarky question to ask you back. It's like, what about k plus one then? Ah, k plus 1 is an integer and is greater than k, so k cannot possibly be the largest integer. In other words, in mathematics, there is no such thing as the largest integer. Okay? Is that okay? Is that concept okay? But in computer science, we do, because you have a limited number of digits to represent a value. When you use the word int, it always has a certain width associated with it. Now, what that width really is depends on the platform of your compiler. If you're compiling code for Arduino, an int is only 16-bit wide. If you're compiling using the 32-bit Intel architecture, an integer is by default 32-bit wide. But if you're using the 64-bit architecture, which is the de facto standard these days, your integer is 64-bit wide. So it kind of depends on the platform and depends on the compiler as well. But you can count on it being fixed width. So what we want to do is now to take a look at what if it is only 4-bit wide? Okay, if I only have 4 bits, what is a bit, by the way? What is the abbreviation, or what is the expanded full phrase of what a bit is? BIT. What does it stand for? You can ask Google, you can ask ChatGPT, you can use a phone if you want. I Binary digit, very good. So the B comes from binary, and then the IT comes from the IT of digit. Okay, so yes, so 1 bit is a binary digit. So now if I say, okay, I only have 4 binary digits, what values can I possibly store in a 4-bit number? So in that case, if you want to, you can enumerate the entire thing. So I'll go through that exercise once so that you can see what it means when I say, okay, let's enumerate, the all the numbers that you can represent using 4 bits. Okay, so 4 zeros. Okay, on this side it is base 2. On this side we have base 10 because we more innately understand base 10. So 0000 in base 2 is not surprisingly 0 in base 10. Yes? Okay. 0001. Oh, that's an easy one too. 0010. Oh, that one is not as easy. What is it? It's 2. That is correct. It's 2 because remember what each digit is representing? Digit 0 tells us how many 2 to the power of 0 we have. Digit 1 tells us how many 2 to the power of 1 do we have. Digit 2 tells us how many 2 to the power of 2 we have. And digit 3 tells us how many 2 to the power of 3 do we have, which translates to 1, 2, 4, and 8. How many do we have for each one of those powers of 2? Okay, are we good with that review of base conversion? Because that's not new. That's a review of base conversion. Okay, so now we move on to 0011. That's 3. 0100 is 4. Okay, so the base 10 side is easy. Okay, so maybe I should just fill that up first and then ask you about the binary side instead. So that's 8, 9, 10, 11, 12, 13, 14. I'm going to stop at 15. All right, so I'm going to randomly pick one row and ask you about it because I want you to show me that you remember how to do base conversion. What is 9 in base 2? Yep, because it has 1 8. and 1, 1. Okay, that makes up the quantity of 9. All right, let's pick something harder. Let's pick 13. What is 13 as a base 2 number? 1, that's 1, 8. So now we have 5 left. It has 1, 4 in 5, no 2. Once we take care of the 4, we only have 1 left. So that's why we only have the 1 left here. Yep. So that's how we do it. Okay. So I'm just going to randomly pick these things to fill in. This one is going to be 1, 0, 1, 1. That is 1, 1, 1, 1. 1 plus 2, 4 plus 4 plus 8 is 15. Going back here, this is easy because if 8 is just 8, this is 0, 1, 0, 1. I do this randomly, intentionally, just so that you guys notice, oh, okay, so we should be able to do this too. Okay, you should be able to do this. Maybe not at the speed that I am doing it because I have done this many, many times already, but you should be able to know how to do this. Okay, and that's all based on base conversion. Okay, which is a module that we have covered already. So now we have a full table telling us with a 4-bit integer, we can only represent 0 to 15. That's it. Is that okay? So this is a concrete example because I just enumerated, which means I just give you a long list of everything that can possibly be represented using a 4-bit number. So what is the next step? The next step that I typically use is abstraction. Okay, this is going back to the document that I showed you earlier, abstraction, because now I want to figure out what a, say, 32-bit number can represent. Okay, are you going to enumerate all the possible integer values for a 32-bit number? So you're shaking your head. Do you want to share with you why you shook your head? So you already know the number of integers that a 32-bit integer can represent, and it will take us a long time to finish that list. Okay, I can write a program to do it, but it will be pointless, right? Okay, very good. So now I want to generalize. It's like, okay, but what is the equation? Okay, if I am given W bits, okay, what is the largest unsigned value? Okay, that's what I want to find out. So how do we go about doing this? So there are two ways to do this. Okay, one way is a kind of graphical way to look at this. So you go like, okay, for the first digit, there are two choices, 0 or 1. For the next digit, it can also be 0 or 1. For the next digit, it can also be 0 or 1. Now remember, if you want to fully populate the tree, it's going to look like this. Okay, so the pattern is every time we add a digit, the number of leaf nodes or the number of the open ends at the end of the whole tree is going to double. In other words, for every digit, the total number of things it can represent is going to double. Oh, doubling means times 2, right? So that means if I have W bits, okay, W representing the number of bits, then the total number of representations it can possibly have is really just 2 to the power of W. But wait, if I ask what is the largest value, you have to remember to subtract 1 from it. And I'll be very clear where you're applying the subtract 1. So it'd be 2 to the power of W, the whole thing, minus 1. Why are we minus 1? Why are we subtracting 1 from it? There are two ways to look at this, but the easiest way is to say, oh, 0 is taking a spot already. So we're counting from 0. We're not counting from 1. Okay? But does it make sense? Okay, this is pretty abstract, and does it make sense? Well, you just have to apply it to the example that we just saw earlier. You say, okay, what if W is 4? If W is 4, then we are looking at 2 to the power of 4, which is 16. 16 minus 1 is indeed 15. So that's a quick check. This is what I call, it's not a proof, it is called a sanity check. Okay, it's just something you can do really quickly and go like, is it consistent with what we have learned up to this point? And it is. So are we good so far with the range of values or the largest value you can represent using the unsigned representation? Yep. Um, what do you mean by smaller? Okay, so do you mean the object code does not take up as much space? Um, so that's a tricky question because there are two sizes, related to a compiled program. One relates to the code portion, and the other part relates to the space that the data, your variables are going to consume. So without forcing the compiler to use a particular width for your integers, then the amount of data space it's going to need will be less than a 32-bit architecture. So you're correct in that respect. However, when you look at the actual code size, which is the instructions, it may or may not be shorter than a larger platform because the Arduino has a RISC architecture, which means it takes multiple instructions to get one thing done, one thing that a Cisp architecture can do in one single instruction. So one can argue that a Cisp architecture, which is your AMD Intel platform, has a higher instructional density as opposed to a RISC architecture. So with the code section, I cannot tell you whether it's going to be shorter or not, but with the data portion, I can tell you it'll be consuming less space. Yep. So there's a certain nuance, to answer that particular question. All right, cool. So now we are going back to the notes. Okay, so now we move on and talk about what about other integer values? How is 19 represented? So this goes to a discussion of a notation called um, let me see. I have to go back and remember the name. Congruent modulo. Okay, that's the term. Congruent modulo blah blah. Okay, so instead of really just explaining this in English, I'm going to give you the mathematical explanation. So the mathematical notation is this, okay? This is the notation, or this is the Wikipedia notation of saying that A and B are congruent modulo n. There's a whole bunch of words and a whole bunch of symbols without any explanation. Yes, I know, okay? In this class, because I'm lazy, I would use a slightly different notation. So I'm going to use this notation to indicate that A and B are congruent modulo n. Okay, that's just me using a simplified notation. But exactly what does it mean? Okay, we see the notation, we hear the words congruent modulo, but what does it mean? Okay, so what it means is a and B, if A and B are congruent modulo n, it means A can be expressed as V times some Ka times n, and B can be expressed as V times Kb times n. V has to be an non-negative integer or natural number. N can be positive or negative as an integer, and Ka and Kb no, I take it back, sorry. N has to be a natural number, and then Ka and Kb can be positive or negative integers. And it's also spelled out here. Ka, Kb are just integers, and then V is a natural number, so is N. All right, so those are the constraints, okay, for A and B to be considered congruent modulo N, okay? So I'm going to give you guys some example and see if you guys can figure out whether those values are modulo congruent some number, okay? So let's go ahead and go through some exercise, okay? Um, Before we move on, you might want to kind of jot down your own notes, okay, of what it means to be modulo congruent something. because otherwise it will be pretty well. I can try to do it so that this is still displayed when I am working on the examples. So I think we can do it that way. Yep, we can certainly do it. Okay, there we go. All right, so let's go ahead. Okay, I'm just gonna clear out all this stuff here. Gonna go back here. All right, so let me ask the question. Are 6 and 23 congruent modulo? Um, mm, mm, this one's a little bit tricky, well, but this is pretty obvious. But I'll let you guys make that determination. All right, what does it mean? It means can we find Ka and Kb? Okay. In other words, I want to express 6 as some number. Okay, we'll call it v plus k1 times 17, and we want to express 23 kind of the same way, but we can choose a different k. This is k2. So the question now is, what is the v and what is the k1 and the k2 in order to make this happen? This one is somewhat obvious, but I'll let you guys think about it. So let's deal with the first one first, okay? So forget about 23. Let's just look at 6. So if I were to say, okay, I want to express 6 as a integer, um, actually, I take it back, a natural number v plus an integer k1 times 17, do you have a whole lot of choices? You do have choices, but the most obvious one is to say, oh, we can make v equal to 6 and k1 to be 0. Is that one way to make it happen? Yes? Okay, so let's just take this one and say, okay, we'll just assume that v is 6 because 6 is a natural number, and k1 being a 0 is an integer. Okay, it satisfies all the requirements. So now the next question is, now that we have fixed the value of v, can we solve for k2? In other words, we know v is 6 already. So we are really asking, can you express 23 as 6 plus some k2 times 17? Can we solve for k2? That's one. Very good. Okay, it is algebra. Okay, this is algebra. So now we can say, oh yeah, we can find another integer k2, which is just 1. So now we have satisfied all the requirements. We have found v as a natural number, k1 and k2 being integers, and we established the equality based on those particular values. So indeed, 6 and 23 are indeed congruent modulo 17. We doing okay so far? Okay. So I'll let you guys kind of chew on this for a little bit, and I'm going to start up my tablet because I want to show you something that a tablet would be the best way to do it. And it's going to take me a little bit of time, so this is a perfect time for you to make sure that you take all the notes that you want to take on this topic. All right. I need this to connect to the same Wi-Fi. And I was having some problems yesterday with this. And okay, it's all good. All right. Um, okay, looks like it should work today. Yep, working fine today. Excellent. All right. So one way to look at this is instead of looking at numbers or integers as a number line, which I think some of you already know the concept, we look at it as a number circle. Okay. So on the number circle, in this case, you're using congruent, congruent modulo 17. The circle has 17 slots, okay? So I can approximate your 17 slots by approximating 16 slots, okay? So this is going to be the only extra slot we need. And then we just chop, 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 chop. Okay, 17 slots right there. So the way you look at this is we know how to label. Okay, if you look at this as a clock, like a really weird clock, you can then label. Oh, okay, we can do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, are we good so far? Okay, there are 17 slots. We start counting from 0. That's why we only count up to 16. Okay, but as the hand or the needle continues to turn, if I want to label what is also known as a 0, but continuing with increasing the integer, what would that be? It would be 17. Very good. So this would be 17, this is 18, this is 19, this is 20, 21, 22, 23. Do you now see how 23 and 6 they fall on the same slot on this clock? That that's one way to visualize what congruent modulo 17 in this case look like. Basically, whatever n, the congruent modulo n is, we just look at it as a clock phase with n slots. Okay, and we are really just turning the wheel over and over again and see if the numbers land on the same slot. Are we doing okay? But you can also, so by incrementing means we are turning the hand in a clockwise fashion, which is conventional. But we can also think of subtraction, right? So in other words, if I say, oh, what is 17 minus 1? 17 minus 1 is a 16 because we are turning the hand counterclockwise in that case, right? So that means when we reach 0 and I turn it some more counterclockwise, what would that be? What is 1 less than 0? It's still an integer. What is 0 minus 1? Negative 1, right? But if I turn the hand, oh, sorry about that. I touched something on the screen. So if we turn the hand counterclockwise from 0, where is it going to land on? The 16. So that means 16 can also be interpreted as negative 1, negative 2, negative 3, negative 4, negative 5, and so on. And then you guys go like, no way, this is absurd. This is like crazy stuff, right? Well, it's not crazy stuff. Okay, so instead of looking at this as crazy, we'll go ahead and say, let's pick some rather large negative values here. So we'll say negative 216, and we want to find out, what numbers are modulo congruent with negative 216. So we'll say this is blah 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 what. Okay, I just need you to find one. Okay, let's just say that we want to find a value that is not negative in 216, that is modulo congruent 17 with 200 negative 216. How would you do that? So what you need to do is to say, how do I express negative 216 as some kind of a v, which is a natural number, plus some kind of k1, which is an integer, times 17 in this case. So the restriction here is v has to be a natural number. It cannot be negative. So how do we find that? Well, there are many ways to do it. Okay. If you do not like the approach of using mathematics to do this, that's fine. You don't have to. So the other way to do this is simply to use, let me go to my Google Drive, and I'll show you, how useful a spreadsheet can be. So now we go to my drive, go to this class, And I'm going to put it into the shared folder, which means, as I work on this, if you want to go to the spreadsheet, you can. So in the shared folder, I will create a new spreadsheet with the name of today's date. So this way it is easy for you to find, oh, okay, this is the kind of stuff that we work on that day. So it's 2025-09-09. And now I just have negative 207, 216, I think. And then on the next row, I just say, okay, let's refer to the previous row and add 17 to it. So now we're closer to 0 or closer to the natural number that I want. So we just keep going like this until we go like, oh, okay, 5 is the V that I want. In other words, all of these numbers that we see in column A, they are all congruent modulo 17 because they're all 17 from each other. We do okay? So 5 is the first one that is not negative. So we're going to say, okay, let's V equals to 5. So if V equals to 5, what is K1? Well, that's algebra again, right? So what we need to do in that case is to say, oh, okay, so we take this number, we subtract 5 from it, and then we divide the whole thing by 17. So I have to go back here, put parentheses around this, and then say divided by 17. So K1 is negative 13 in this case. Are we doing okay so far with how I kind of brute force my way into figuring out, oh, this is V, and if this is V, this is going to be my K1. Are we good with all that? Cool. All right. So that is the whole concept of congruent modulo something. So you might be asking, why do we have to know this stuff? I mean, this is all math stuff. This is a computer science class. To that question, the first answer is computer science is a subfield of applied mathematics. As much as some of us do not want that to be the case, that's the truth. Computer science is a subfield of applied mathematics. Okay? But to answer the other question, which is from our context, why is this important? Well, that's exactly the flow of the module. So the way we look at this is we look at this table here. Okay, so now we go back to some more sensible n, which is modulo 16 in this case. So in modulo congruent modulo 16, we can now see how if kb is a negative one, then 0 A is 0. A is congruent modulo 16 with negative 16. 1 is with 15 and so on. But when you look at the other half, 8 is congruent modulo with negative 8. 9 is with negative 7 and so on. All right, so this is not easy to read because it's not a circle. So what we'll do is take a look at this as a circle. So let's go back to Supernote. And on the next sheet, we'll take a look at the circle. So now we look at another number circle, like so. And this time it is 16. There are 16 slots to it. Okay. And we'll number in the inside the unsigned interpretation of each slot. Are we good so far? Now, remember what I said. I said the inner number is an interpretation what that slot means. In other words, the slot can have multiple interpretations. Okay? So now I go like, okay, if negative 1 is to exist on this number wheel, where is it going to be? Can someone tell me where negative 1 is going to be if it is represented in this number wheel based on congruent modulo 16 math? It'll be the same spot as 15. Okay, very good. Okay, so -1, -2, -3, -4, -5, -6, -7, and -8. So that means the same slot, which is identified by a single 4-bit pattern, can be interpreted as one of two things. So let's just pick this one here, okay? So if I were to look at 12 and look at the bit pattern of 12, it is 1100, okay? So that means if you see the bit pattern of 1100, you can interpret it as 12. You can also interpret it as -4. The same bit pattern can be interpreted in multiple ways. Is that concept okay? Okay. And it does make sense because according to congruent modulo 16 math, -4 and 12, they fall onto the same slot. So it does make sense that both of these can be the interpretation of the bit pattern of 1100 as a base 2 number. Yes. Okay. Oh, I like that question. Okay, so let me kind of re-mention the question, which is the key is how do we decide which way to interpret 1100? Am I capturing the question? Okay. Okay. So I'm gonna uh, ask you back a question that may seem to be impolite. Okay, it may seem like I'm challenging you, but that's not the intention. I just want to kind of give you some warning about that, which is so I'm gonna ask you back. What do you care? What? Why do you care whether 1100 is representing -4 or 12? So, okay, and when does it matter? When does it make a difference? Yeah, but when does it matter that a particular bit pattern is interpreted in one way or the other way? Okay, so I meant to not to challenge you, but I meant to kind of have you to think about. But why am I even asking the question? When does it really make a difference whether 1100 is interpreted as 12 versus -1? So let me show you an example of why in most cases we really do not care. Okay, so I'll show you an example on the next slide. So on the next slide, I'm going to give you an example of 1100 plus 0001. Okay, we'll just make it super easy, okay, because the whole point is not to perform binary addition. The whole point is what is the result? Does it really matter whether we look at it as signed or unsigned? Okay, so we look at this and go like, okay, this is X, this is Y, this is Q, this is K, this is S, okay, and we learned all this stuff already in the previous class, so you should be able to do this with me. This is the exclusive OR with the previous two row. This is always going to be 0 because it is the least significant digit. This is going to be 0 because 0 plus 1 does not have a carry of 1. 1 plus 0 does not have a carry of 1. 0 plus 0 is a 0, or 0 or 0 is a 0. Same thing over here. That's going to be 0. This is 0. This is 0. And then now we have just the exclusive OR between the Q and the K, and we get our sum. Okay. So now the question is, well, if we interpret 1100, if we use the unsigned interpretation, then we are looking at 12 plus 1, which is supposed to be 13. Hey, that works out. This is indeed the bit pattern of 12. This is indeed the bit pattern of 13. Works out. What if we look at it as -4? -4 plus 1 is supposed to be -3. So now you go like, okay, is 1101 representing -3? Yep, until in one specific case, until you compare. Okay. In other words, okay, let me make it more clear what I mean by compare. When I ask you 1100 as a bit pattern, is it greater than 0001 as a bit pattern? Then it matters. Because if you use the signed interpretation, which means 1100 is representing -4, then -4 is greater than 1 is false. On the other hand, if you use the unsigned interpretation, in which case 1100 is representing 12, then 12 is greater than 1 is true. That is the only time when it matters how we are going to interpret the bit pattern. Is that okay? Okay. So this part is it's tricky because in C++, it is not up to the moment that you compare that you have to say, oh, this is signed and that is unsigned. Okay. As soon as you declare a variable, it's either int or unsigned, right? So the type or how you interpret the bit pattern is associated with the variable itself. So anywhere the variable goes in the expression, in the comparison and whatnot, you already know, oh, this is supposed to be signed or this is supposed to be unsigned. In assembly language programming, that is not the case. How you add, how you subtract are identical whether you're dealing with signed versus unsigned numbers. How you compare is actually the same, whether it is signed or not. It is the side effect of comparing and which way. Okay, this is a little bit ahead of us. Okay, so when you compare two bit patterns, it will set a bunch of what we call flags or bits. Okay, so which bit do you use to make a decision? That is when you say, oh, we are interpreting it signed versus unsigned. Okay, but that's the next module, which is binary comparison. That's the next module. Yep. So I'm giving you guys a little preview of how this is becoming useful later on. Okay, very good. So, but are we doing okay so far with everything up to this point? Okay. So I like that question, so if we look at 1100, is it -4 or is it 12? The answer is, why do you care? Are you comparing? Because if you're not comparing, then we don't really care. Addition and subtraction works exactly the same way, whether you interpret it signed versus unsigned. But when you compare, then it does matter. All right. So this is a good discussion. I like it. Okay. So now we move on and say, all right, this is all cool. So how do we um, perform arithmetic negation in base 2? So what is arithmetic negation? In base 10, it's super easy. You'll say, oh, the negation of 10 is -10. The negation of -10 is 10. Is that okay? So that's arithmetic negation, which is distinct from logical negation, which is the not operator. So how do we do it in base 2? So we first start off with this statement, which has to be true. In other words, the negation of some value v is congruent modulo n with the same value plus k times n. That has to be true. I have to be able to find a k to make this happen, because that k just has to be 0. That's right. Okay, so we don't have a problem with this statement. Okay, the negation of a value is congruent modulo n with the negation of the same value plus k times n for some k, because that k is just 0 in this case. So now what we do is we look at this little chain of reasoning. So we'll consider the case when k equals to 1. So that means, um, so if we use 1 instead of k here, then we are basically saying negative v is congruent modulo n with negative v plus n. Okay, so we'll just kind of pause here to make sure that we all understand what I mean by that. Are we doing okay so far? Because as long as this k is an integer, whatever comes out as the value on the right-hand side is still congruent modulo n with negative v, or the negation of v. Is that okay? So k can be 0, that's the easy one. It can be -5, can be 16, can be 13, doesn't matter. As long as k is an integer, we have established the congruent modulo and thing, right? Okay, so now we move on to the next one. So you can see how I switched from modulo, congruent modulo n to just equality, because this one is really just equality. Negative or the negation of v plus n can be re-expressed as the arithmetic negation of v plus n minus 1, the whole thing plus 1. It's like, tag, what are you doing here? You're making something simple, which is n, into something that is unnecessarily complex, which is n minus 1 plus 1, with parentheses. That seems really stupid, right? But it's going somewhere. Okay, so now we move on to the next equality. Okay, so I'm gonna move my equality over here, which is equally stupid for those of you who are really good at algebra. You go like, Tag, what are you doing? Because this expression is algebraic speaking, you can derive it into here. Are we agreeing on that? Yes? Okay. So it's like, okay, fine, Tag, you're just making things worse. Okay, your things are used to be a lot simpler, which is really just the arithmetic negation of v plus n, and now you turn into a beast. Okay, which is n minus one, the whole thing minus v, and then that whole thing plus one. What is the whole point? Okay, the bottom line is now we have established a congruent modulo n between the arithmetic negation of v and the last form of the equation over here. You go like, so what, right? Well, the thing about this is our n is not just any integer or natural number. Our n here is always going to be a power of 2. In other words, n cannot be 13, it cannot be 36, it cannot be 60. It has to be a power of 2, which is like 2, 4, 8, 16, 32, and so on. So you go like, okay, so what is the big deal of that? So now we move on to the next few paragraphs, okay? So we know that n is some power of 2. Let's call it w, okay, for some w that is greater than 0. So, hmm, so that's an easy one, right? Instead of n over here, we just substitute n with 2 to the power of w, because n equals to 2 to the power of w. That's just a simple substitution. Are we good with that? Are we still following? Okay, okay. So now we go like, okay, so what is the big deal? The big deal is when you are looking at subtracting one from a power of 2, the pattern that you end up with in base 2 will be all ones. Okay, I just use a lot of words that you understand individually, but did you understand the entire sentence? Let me say that one more time. Do you want me to say that one more time? Okay. When you subtract 1 from a power of 2, the resulting difference, if you express it as a base 2 number, is going to be all ones in base 2. Okay, best to illustrate it with an example. So we'll go back to the super note over here. So pick a power of 2, pick a power, okay? I'll let you guys choose between 3, 4, 5, and 6, okay? That would be the power that we are, that would be the W, okay? So pick one. 6, okay, fine. W equals to 6. So 2 to the power of W is going to be 64. And so 64 minus 1 is 63. So I'm going to say that 63 is going to be 6 ones in binary. Okay, so I would say 63 is 111, 111 in base 2. Okay, I see you guys are just nodding. Are you sure? Are you sure that 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals to 63? Yep, yes, but there's a reason behind it which I'm not going to prove in this class because yeah. Okay, so, okay, fine. So when n equals to 2 to the power of some w, then whatever n minus 1 is always going to be something like this. Okay, so let me add one more thing that is also going to be helpful. When you subtract anything from all ones, okay, it doesn't matter what the bit pattern is. Okay, so I'm just going to say D3, D2, D1, D0. Okay, those are the individual bits. I don't have to go through the whole long process of Q, K, or Q, T, and D in this case. D is just a digit in this case, okay? So it's not the difference. So whatever goes here is going to be the negation of D0 as a binary, as a Boolean. This is the negation of D1. This is going to be a negation of D2. And this is going to be a negation of D3. Are you convinced? How do you convince, how can you be convinced that 1 minus some x, which is a binary digit, is the same thing as the negation of x? X is a binary, so that means it can only be a 0 or 1. How do we prove this? It seems to intuitively make sense, but how do you prove it? I'm expecting a phrase that you guys are going like, no, not that thing again. Yes. But go ahead. Tell us what you're thinking. Hmm. Yep, exactly. And the best way to visualize it is a truth table. Yes, it's that thing again. Dang it, truth table. When are you gonna stop talking about truth table in this class? I'm gonna tell you, not likely until the end of the semester. Okay, so let's go ahead and take a look at the truth table. X is the independent variable. It can be a 0 or 1. Okay, the negation of x is 1 versus a 0. Is that okay? And now we look at 1 minus x. Okay, 1 minus 0 is a 1. 1 minus 1 is a 0. Are we good so far? Okay, so how does this have anything to do with what we are talking about? Well, there's one more step, okay? So what this really means is 1 minus a particular integer, I shouldn't say 1, but 2 to the power of w, the whole thing minus 1, this thing minus a w bit number. Let's call that number x. So in this case, this x here is a w bit wide integer. Okay, is that okay? So I'll just make it very clear. This is a w bit pattern. Here we go. This is the same thing as the bitwise not of x, which in C is tilde. I know tilde is not one of the operators that is likely to be covered in CISP 360, but that means bitwise not. Bitwise not is doing exactly what this is doing. You are negating every single bit that is given to you individually. That's bitwise not. Are we good so far? And then bitwise not is also called the ones complement of x. That's just a name. All right. So with this, now we switch back to the notes and go like, how, what, what is going on here? We don't understand. Okay. So we'll just take a look at a concrete example here. So we look at -3 and then we express it as, because we're dealing with 4 bits. So W is 4, 2 to the power 4 is 16. So that's why we got the 16 here. 16 minus 1 is a 15, and we subtract 3 from it. So over here, we also, this is actually a proof to show that, it's the same thing as the negation. So now we can skip that proof. Okay, it's not important to go through that proof. So now we can make this conclusion here. This is the bottom line. Um, the arithmetic negation of v is congruent modulo with congruent modulo 2 to the power of w with the bitwise not of v plus 1. The bitwise not of v comes from this thing here because 2 to the power of w minus 1 gives us all ones as a bit pattern. And when you subtract any bit pattern from all ones, it is the same thing as a bitwise not. So that's why we can now make a conclusion about if you want to figure out what is the arithmetic negation of a bit pattern v, it would be the same thing as performing a bitwise not of v and then add 1 to the end result. So if you don't fully understand the math in between, it's okay. Okay, I want to include the explanation of how it works because if I was a student, I would want to know it. Okay, so but if you're not interested in the actual math in between, it is okay. It is not going to hurt you in this class. But if you go back to the 5 dimensions that we talked about earlier in this class, all the reasoning relate to at least a few of the 5 dimensions. Okay. Yep. Exclusive OR. Yep. So that one, so all that explanation is based on our Boolean operation based multi-digit base 2 subtraction. But it's kind of the same explanation. Eventually, it is the same explanation. Okay. So now, we also explained in terms of notation that C1 is called one's complement. One's complement of x is the same thing as bitwise not of x. And so 2's complement of x is the one's complement of x plus 1. That's just a definition. That's just a name given to this particular operation here. All right. So we still got plenty of time. So we're going to work out a few examples so that you guys can see how this actually works out. All right, so we are going to, so give me a negative value between -1 and -8. Pick one of them. And -4, okay, so we'll take -4. So we'll say W equals to 4, which means we're dealing with 4-bit numbers. And we are working with V is going to be 4 because we want to figure out what is the arithmetic negation of 4. Yep, I have to switch the tab. Thank you. There we go. So V is 4. We want to find, the we want to find what is the bit pattern representing the arithmetic negation of 4, which is really just -4. Is that okay? All right. So we now say -4 is the same thing as the C2 of 4. But 4 is a base 10 number. I really can't perform bitwise operations using a base 10 number. So now we're going to say the negation of 0, 1, 0, 0 in base 2 is the C2 operation applied to 0, 1, 0, 0 in base 2. Is that okay? That's just base conversion. Because you cannot perform 2's complement on anything other than base 2 numbers. Are we good? All right. So now we say, but exactly what is the 2's complement of a bit pattern? Well, that translates to this one's complement of the same bit pattern plus 1. What is one's complement? Oh, it's the same thing as a bitwise not. What exactly is a bitwise not? You look at every single individual bit and you flip each one to the opposite side. So 0, 1, 0, 0 becomes 1, 0, 1, 1. In base 2, the whole thing plus 1. Are we okay with that step? Are we okay with the application of one's complement, which is flipping each individual bit at its own position? Are we good? All right. So you perform this addition, and I probably could show you the longhand of doing this, but I'm just going to say this is 1, 0, 0 in base 2. All right. So now the question is that really the case? Because -4, does it have a bitwise, does it have a binary representation of 1, 1, 0, 0 in base 16, or using only 4 bits? Well, let's go back to a few slides. Okay, so 1, 2, 3. There we go. We're looking at -4. Oh, it is indeed 1, 1, 0, 0. Are we good so far? So once again, this is not a proof. This is what I would call a sanity check to make sure things are consistent. So what do you know about arithmetic negation? If I take, if I start with a value of v, and I take the arithmetic negation of the arithmetic negation of v, what do I get? In other words, I'm asking you, if I take the arithmetic negation of the arithmetic negation of some value v, what do I get? I get v back. I should get v back, right? So now we're going to use that to also perform another sanity check and say, hey, if I apply 2's complement to 1100 in base 2, I should get back 0100 in base 2. Does that make sense? Because I claim that this is the way to perform arithmetic negation. So if I apply the same thing and say C2, oops, sorry, C2 of 1100 in base 2, that translates to C1 of 1100 in base 2, the whole thing plus 1. Then we are just flipping all the bits, right? Zeros becomes ones and ones become zeros. So now we have 0011 in base 2 plus 1, which indeed is 0100 in base 2. Okay, so the sanity check passed. Okay, it is not the same as a mathematical proof. It just means things seems to be consistent. So are we good so far with 2's complement? We good? Yep, go ahead. Mm-hmm. Right. That is correct. But why does it like that? Why does it behave like that? It has to do with how we derived the whole thing. So let me just kind of interject this before continuing. The whole thing works because the whole principle is really just doing this. We are turning the whole wheel by one full circle if we should come back to the same spot. It's just that in the process, I converted the whole thing several times and applied several techniques in the process to come up with C2 or 2's complement. But it's based on doing this, which translates to this. Okay, so go ahead. Sorry, I kind of interrupted you. Hmm. That's exactly what it will do. Yep. So when you perform addition and you have reached the largest number that is possible, the next add one will go back to 0. Okay, so let me just kind of expand on what I just said. So what I'm saying, but it is related to what we are doing, but not exactly. Okay, so but I do want to illustrate it. So when you say what is 1111 plus 0001, then this time I'm going to do the long version. So we have x, y, q, k, s. So this is a 0. 1 plus 1 has a carry of 1. The exclusive or between 1 and 1 is a 0. 0 plus 0 is a 0. 1 plus 0 has a single digit sum of 1. 1 plus 1 has a single digit sum of 1 with a carry of 1. And you will see the same pattern over here, same pattern over here, and we'll end up with all zeros here. So that means when you look at what is 1111 plus 1, it goes back to 0000 with an overall carry of 1. So that's why this is what we call wrapping around. So when you're writing a program in C++ and somehow you end up with an endless loop and you did not exit the loop, your condition is wrong, okay, it will wrap around. Eventually the number goes back to 0. If you add 2, it is not necessarily the same thing. It depends on the condition. So I will extend. I will basically give you guys another example, and then we'll move on to the lab portion. Okay, so I will show you a program that you all understand already, but then once if you don't understand how integers are represented and the wrapping around effect, then you go like, no way, this program is not going to exit, but it does. So we'll go ahead and take a look at a program that is mysteriously exiting the loop when it's not supposed to. Okay, so we'll just call this bad loop. And I don't need anything else. There we go. Unsigned um, x. Okay, and we'll say x starts with a value of 5 while x is um, greater than 3. Okay, so 3 is fine. Um, plus x. Okay, so look at the logic of this code. It is insanely stupid because x starts with a value of 5, and I say as long as x is greater than 3, we are staying in the loop and we make x even bigger. So if you present this to a um, CISP 300 student, the CISP 300 student, a good one, would point out and say, that's going to be an infinite loop because there's no way x is going to be ever not greater than 3 anymore. Okay, it's just stupid. But if you run the program, it does exit. It will exit. So let's go ahead and do it. So we'll do a compile, bad loop. This is actually how I write my program and test my programs. I do everything on the command line. Okay, it might take a while, but it exits. That's because it reached all the way to the end, which is the largest possible unsigned value of an int, however wide it is. It then wraps around to 0, and then 1, and then no, it wraps around to 0, and that's how it exits, right? Because 0 is not greater than 3, then it exits. So this is what I'm trying to connect to this class. Okay, so what you have learned, even though a good portion of it seems to be like, oh man, this really sounds like unnecessary complicated math. Okay, but the outcome of the understanding of how numbers are represented in a computer can really help you debug programs like this. Now, am I implying that you guys are stupid like I am making code like that? No. But eventually somebody's going to make a mistake turning a greater than into less than, and then you end up with situations like that. Are we good so far? All right. So let's go back and work on the lab. So today's lab is on addition. So that depends on how well you understand addition in general. Um, it's a good test. Okay, so you can think of every single lab as a super low stake assessment to evaluate whether you are understanding the material sufficiently or not. Okay, so if you're struggling with a lab, it might be a pointer to say that you might want to kind of use a different strategy when it comes to this class. Okay, I'll just kind of put it that way. We do have tutors in the Mesa Center, on the first floor. So for those of you who qualify as a Mesa student, you can go ahead and try that out. I think that resource is really good. And of course, I have to tell you what is the access code. Oh, I know what the access code is. So the access code of this particular activity is also a test to see whether you have been following along with all the material, because the access code is X, Y, Q, K, S. So for people who look at this and go like, "Oh yeah, that's funny," well, congratulations, you have shown me that you have been studying and understanding the material. Okay. For people who look at these 5 letters and go, like, "I have no idea why you choose these 5 letters to be the access code," I'm gonna have to say, you might need to review the material a little bit more. My Monday, Wednesday class is one lab ahead of the Tuesday, Thursday class. Um, this is not a challenge, okay? So don't try to push yourself. I think one of my students in my Monday, Wednesday class was done like within 10 minutes. It's like, is that it for the lab? I go like, yeah. All right. So I'm gonna stop the recorder, get it uploaded. But before that, I'm gonna go get some water.